Hello everyone, welcome to the 7th video in this series. We start with problem number 61. A thermal neutron having speed v impinges on a uranium nucleus. The reaction cross section is proportional to. We know the absorption cross section of thermal neutron is inversely proportional to its velocity. So option A is the correct answer. Problem number 62. The approximate force exerted on a perfectly reflecting mirror by an incident laser beam of power 10 milliwatt at normal incidence is. We know the force F is given by 2 times I divided by C, where I is the intensity. Let's put those values. So this is equal to 2 times 10 to the power minus 3 watt divided by 3 into 10 to the power 8 meter per second. So this is 2 by 3 times 10 to the power minus 10. So it's approximately 0.6 times 10 to the power minus 10, which can be taken as 6 into 10 to the power minus 11 Newton. So option B is the correct answer. Problem 63. A circular loop of radius r carries a uniform line charge density lambda. The electric field calculated at the distance z directly above the center of the loop is maximum if z is equal to what? So we know the formula for the electric field of a circular loop depends on z in this following way. So what we will do, we will calculate the first derivative of Ez with respect to z and set it to 0 and find the value of z. Let's do that. Let's take the derivative. So using the chain rule, this is z square plus r square to the power 1 by 3 minus 3 by 2 z square by r square 5 by 2 times 2 z square is equal to 0, or z square plus r square minus 3z squared is equal to 0, or z is equal to r by square root of 2. So option B is the correct answer. Problem 64. A charge plus q is kept at a distance of 2r from the center of the grounded conducting sphere of radius r. The image charge and its distance from the center respectively are. So we recall the formula. The image charge q prime is equal to minus r by a times q, and the distance of the image charge b is equal to r squared by a. Here a is the position of the charge. In this case it is 2r. Let us find q prime. This is equal to minus r by 2r times q, that is minus q by 2, and p is equal to r squared divided by 2r, that is r divided by 2. So we find that option D is the correct answer. Problem 65. The capacitance of two concentric spherical metal cells with radii A and B is. So we recall the electric field between the two concentric metal cell is given by q divided by 4 pi epsilon naught r squared. This can be found simply by using Gauss theorem. Now we find the voltage difference between the two spherical metal. So V is given by minus integral of E dot dr from B to A. Let us calculate this integral. Thus V is equal to minus q by 4 pi epsilon 0 B to A 1 by r squared dr, and the integral is minus 1 by r a to b. Thus V is equal to q by 4 pi epsilon naught 1 by a minus 1 by b, which simplifies to q 4 pi epsilon naught b minus a divided by ab. Now the capacitance C is given by q divided by v, which is equal to 4 pi epsilon naught AB divided by B minus A. So option B is the correct answer. Problem 66. Two spherical cavities of radii A and B are hollowed out from the interior of a neutral conducting sphere of radius r. At the center of each cavity, a point charge is placed. Called these charges plus QA and plus QB. Find the surface charge density sigma A, sigma B and sigma r. So let us consider a Gaussian surface, a sphere that just encloses the first cavity. Since this Gaussian surface is inside the conductor, the electric field will be 0. And according to the Gauss law, the net electric charge inside that Gaussian surface would be 0. Thus, the charge minus QA will appear on the surface of this cavity. Thus, the surface charge density sigma A is equal to minus of QA divided by 4 pi A squared. Similarly, considering another Gaussian surface just outside the second cavity, we can find the surface charge density sigma B is equal to minus QB divided by 4 pi B squared. Let us now find sigma r. To find this, we consider another Gaussian surface just outside the sphere of radius r. Now note that inside this Gaussian surface, the net charge is 0. So is true for this Gaussian surface. But when you look at this, there is a total charge of plus QA plus QB. And that charge must be on the surface of this conductor. So sigma r is equal to QA plus QB divided by 4 pi r squared. So option A is the correct answer. Problem number 67. A long cylindrical conductor of radius r and sigma is equal to infinity carries a current I equal to I naught sin omega t. The conduction current density Jr for r greater than capital R is. So the situation is like this. We have a cylinder and the current I flows through it as I equal to I naught sin omega t, and you have to find the conduction current at J at small r, which is greater than capital R. Since no current flows through this, so the current density will be 0. So option D is the correct answer. Problem 68. A diffraction grating used at normal incidence gives a green line at a certain order superimposed on a violet line of the next higher order. If the angle of the diffraction is 30 degree, the number of lines per centimeter of the grating is what? So we use the grating equation d sin theta is equal to n lambda. So for the green line we have d sin 30 degree, that is half, is equal to n say lambda of g, and for the violet line we have d sin 30 degree, that is half, and equal to n plus 1 times lambda v. So n plus 1 is because the next higher order. So from these two equations we have to eliminate n. So let's do that. So from the last equation we write d by 2 is equal to, and now we replace n by d by 2 lambda g plus 1 lambda v, and this is simplified to d by 2 1 minus lambda v divided by lambda g is equal to lambda v, or we want to calculate n, that is 1 by d, and this is equal to 1 by 2 lambda v 1 minus lambda v divided by lambda g, and let's simplify this further. So lambda g minus lambda v divided by 2 times lambda v lambda g. So let us put the values. So lambda g is 540 nanometer minus 405 nanometer. 2 times 540 times 405, the unit would be in the nanometer. Let's take that let's convert that to meter, that is 10 to the 1 minus 9 meter, and we need lines for centimeter. Be careful to add a square 10 to the power square 10 to the power 2 here. So this is per centimeter now. So if you calculate it, it is 3086 per centimeter. So option D is the correct answer. Problem 69. The input Vi to the following circuit is a square wave as shown in the following figure. Which of the waveforms is the best suitable output? So you note this configuration. This is differentiator op amp. So the output would be V output is equal to minus of RC times the derivative of the input signal. So the input signal is a square wave. So when you have this sudden change in the signal, you will observe a spike. So you will observe spike here, 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 as well as here. So option C is the one which has spike, but I was expecting the phase difference between the input and the output signal due to this minus sign. Anyway, option C is the correct answer. Problem 70. A long straight wire carrying a uniform line charge density lambda is surrounded by rubber insulation out to a radius capital R. The electric displacement at a distance r greater than 0 from the axis of the wire is. So we have the following situation. Here this radius is capital R and this is the point, this is the line charge with density lambda. So we consider a cylindrical Gaussian surface with radius r and we use the Gauss law. So d times 2 pi r, that is the circumference of this circle, times L, that is the height of this cylinder, is equal to the free charge inside, that is lambda times L, or d, the electric displacement, is lambda times 2 pi r. Now from the symmetry of the problem, so we can find the direction would be radially outward. So d as a vector is this times the unit radial vector. So option A is the correct answer.